We discussed in Lecture 10 how a black hole has no hair. As viewed from the outside, the only discernible properties of a black hole are its mass, spin or angular momentum, and electric charge. Regardless of what you threw into a black hole, they all look the same. So trees, people, phone books, dinosaurs, stars, frogs, or anything else, it wouldn't make any difference at all. Only the total mass and spin would remain, or a bit of charge if the thing is not electrically neutral. So black holes have no hair. You can have a little road sign like this, no stopping here, no hair grows on black holes. Now this applies even to a black hole made out of antimatter, because antimatter has regular attractive gravity. So whatever information was contained in the matter that fell into a black hole appears to have been lost from the rest of the universe. This, in and of itself, might not trouble you so much. After all, you could lock, a bunch of items in a vault and then die, and nobody would know what's inside. But in fact, the information seems to be permanently lost from the universe. After the black hole evaporates, due to the Hawking process, all we have are thermally emitted photons, and they carry information only about the temperature of the black hole, which is inversely proportional to its mass. This conclusion seems to violate a basic principle of quantum mechanics that no information is ever truly lost from the universe. It only gets scrambled or hidden. So, what's going on? Is information truly destroyed or not? Does the no-hair theorem plus Hawking evaporation spell the end of quantum mechanics? Well, there are four possibilities that theorists typically consider. The first is that information really is lost in a black hole. Quantum mechanics is violated. Secondly, perhaps, when a black hole evaporates, the Hawking radiation carries the information in some subtle ways out of the black hole. The third possibility would be that a black hole can never completely evaporate. Perhaps it leaves a small object behind that stores all of the information that ever went into that black hole. And the fourth possibility is that the black hole connects up to some other universe, as we've discussed, perhaps through a wormhole, and that's where the information goes. It goes zapping over into that other universe. Now let me argue against the third possibility. If only a tiny object is left after most of the black hole evaporates, it really shouldn't be able to store an arbitrary amount of information in something arbitrarily small. And the argument against the fourth possibility is that if the black hole connects up to another universe where the information goes, it is still destroyed as far as our universe is concerned, right? We don't see it. Quantum mechanics in our universe appears to be violated. And we know of no way to test for the presence of the other universe. So whether the universe really does have that information or not is unknown to us. We can't know. So for several decades, the conclusion of most general relativists was that information really is destroyed during black hole evaporation, and that the predictions of quantum mechanics fail in this regard. Well, that would be, pretty striking news. Quantum mechanics failing, but maybe not so striking since it's failing in a way that has to do with general relativity, and we don't really have a quantum theory of gravity yet, so perhaps that failure is not so fatal. Indeed, Stephen Hawking believed that information is lost, as did Kip Thorne at Caltech. But a few physicists disagreed. They felt that there is something incomplete in the Hawking calculations. Hawking radiation must be modified to be consistent with quantum mechanics. Among the people that believed this were Don Page of the University of Alberta in Canada, John Preskill at Caltech, Gerard 't Hooft at Utrecht University in the Netherlands, and Leonard Susskind at Stanford. In fact, in 1997, Kip Thorne and Stephen Hawking bet John Preskill, an encyclopedia of the winner's choice, that information really is lost when it goes into a black hole. This is a high-stakes bet, folks, okay? Well, recently, this long-standing information paradox may have been resolved. It appears that information does indeed emerge out of the black hole as part of the Hawking radiation. Moreover, we conclude that everything in the universe, maybe like a hologram, or at least mathematically equivalent to a hologram. And rest assured, I'll define what I mean by all these terms. That's the point of this lecture. Well, whoa, boy, this is weird stuff. Not at all conceptually easy, right? This is going to stretch your imagination to its limits, okay? Well, don't worry about the details. I'm just going to present a short, basic explanation. And, this is, after all, one of the most challenging ideas from all of recent physics and astronomy. So don't be concerned if you're initially confused or remain confused. There's much more material presented in two popular books by Leonard Susskind of Stanford University, one of the people who played a huge role developing this new revolution in physics. The first book is called The Holographic Universe, An Introduction to Black Holes, Information, and the String Theory Revolution. The other one is called The Black Hole War, My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics. This lecture that I'm giving here is based most specifically on the second of these two books, The Black Hole War, although of course in just half an hour I have time to present only a small subset of the entire material. Okay, let's get started. What is information? Well, information is a set of data that completely describes a system, distinguishing it from all others. It could be letters on a page, but letters themselves have many shapes and carry much information. They're just not basic enough. Computers use the binary system, ones and zeros. These are bits. The ones and zeros are called bits. A bit is a single unit of information. It cannot be reduced in size. Now, you could have instead used the dots and dashes of the Morse code, for example. The total information of a large object consists of all the bits of information that would be needed to completely describe it. So a giraffe, for example, consists of a huge number of bits. Or if I take a glass of water like this with a very large number of molecules in it, you could have a long series of ones and zeros that describe the positions, speeds, and properties of all the water molecules. That would be a truly huge amount of information. Now, you could have many similar arrangements. Any other specific arrangement of water would also have a huge information content, but it would look broadly similar on large scales. It might be entirely impractical to measure all the microscopic positions. So in that case, you'd have a whole bunch of hidden information. The information is there, but you don't really need to even know what it is because macroscopically all the configurations look about the same. In that case, we say that the glass of water has high entropy or disorder. You can't tell where all of the other molecules are and what they are doing microscopically if you just measure a few. All the others are in random positions. They don't care what the few that you measured are doing. So there's lots of scrambled or hidden information in this case. But now suppose I suck the energy out of the glass of water and freeze it. Then the entropy, the amount of disorder, goes way down. Okay? Suppose the ice forms a cubic lattice. Now, ice generally forms a hexagonal structure, but let's use cubes for simplicity. The cubic lattice might look something like this. If I know its structure, if I know the structure of ice, then by measuring just a few of the molecules, their positions and their motions, I can predict where all the others are and how much they move, which would be not much, by the way. So there's low entropy in such a system. There's the same amount of information as before, but I don't have to measure each molecule because by measuring just a few, I can tell where the others need to be. If now I take a glass of water, like this, and I put a drop of food coloring in it, initially the food coloring will be in pretty much one location, and you'll be able to describe this without measuring each and every molecule. Let's try this. And you put the food coloring in. The food coloring forms this droplet, which is spreading out, but at least initially it was relatively confined to a certain area compared with the rest of the water. I could do it again, like that. The droplet is initially confined, so you don't need as many measurements to determine where all the molecules are. That's relatively low entropy. But now if I mix the food coloring uniformly through the water, now it all looks mixed together, and Many different configurations would lead to this same general appearance. This would have a very high entropy compared to when the food coloring droplet was all in one place. So the food coloring diffuses through the water and becomes uniformly distributed. The information about the position and motion of each molecule is still there, but it got scrambled. It's a state of high entropy. I could measure it, but that might be impractical, and I don't need to because it always looks the same. So, in fact, no information gets lost. All the particles have a position, a speed, some properties, but I don't really need to know what they are. A basic principle of physics is that information is never destroyed. It just gets scrambled or hidden, thus increasing the entropy or the amount of disorder in a system. Otherwise, the laws of physics would look different if one were to reverse the arrow of time, yet they are thought to be the same. Microscopically, if you reverse the arrow of time, we think that you really couldn't tell the difference. There's nothing particular about the arrow of time that distinguishes one direction from another, other than the general increase of entropy, the second law of thermodynamics, which we discussed in the previous lecture. Now, you might think that in quantum mechanics, information is destroyed, not conserved. After all, particles are described by some sort of a weird wave function from which one can calculate the probability that they are in various specific states. You might think that the result of any specific measurement is not certain, but rather probabilistic. That's what quantum mechanics teaches us. But in fact, in a microscopic way, it's the opposite. In quantum mechanics, the evolution, the temporal evolution of the wave function is deterministic. Information about a system is conserved, not lost. If you don't disturb the system, you can predict exactly how the wave function will change with time, thus allowing you to predict the statistical outcome of many future measurements. This is a fundamental principle in quantum mechanics. Now let me give you an example to clarify this difficult abstract concept. Suppose you have a source of light that emits a photon toward an opaque sheet of metal having a tiny hole in it. Okay? Behind the hole is a screen coated with phosphor, which lights up when the photon hits it. The photon may go through the hole, or it may bounce off the opaque screen. If it goes through the hole, it will hit the phosphorescent screen, creating a small flash, but generally not at the position opposite the hole. Because in fact, in going through the hole, you have essentially localized the photon in space. You know where it was. And according to the Heisenberg uncertainty principle, discussed in Lecture 10, you would be giving a random kick to the photon. The mere measurement of the photon going through the hole must impart a random kick to it, making its momentum uncertain. So now let's remove the screen of phosphor and redo the experiment. Again, the photon will either go through the hole and get a random kick, or bounce off of the opaque sheet. Without a phosphor screen to detect the photon, it's actually impossible to know the position and motion of the photon. Now suppose we imagine reversing the photon's path, going back through the hole toward the light source. Will the photon return to its original location, where it was emitted from the light source? Well, one might think that the apparent randomness of quantum mechanics ruins the conservation of information, so that the photon doesn't return to its original location. But in fact, the answer is weird. If we make no attempt to look at the photon, that is, to determine its state of motion and position before we reverse the motion, the photon will return to its original location. Information will have been conserved despite the seeming unpredictability of quantum mechanics. On the other hand, if we do look at the photon with the phosphor screen before reversing its motion, the final result will be random. The photon will generally not end up at its original location. A measurement will have been made, and we, the observers, will have permanently altered the state of the photon, resulting in an apparent loss of information. Now, it turns out that if we take into account the quantum mechanical wave function of the entire system, including the photon and the observer, then there is no loss of information even if a measurement is made. But that's a much more complex system than the photon alone. I want to shy away from it for the purposes of this lecture. So considering the photon alone, Information seems to be lost if we disturb the system, and not lost if we leave it alone, despite the apparently probabilistic nature of the quantum world. Okay, so let's get back to black holes. As I said in the previous lecture, Jacob Bekenstein reasoned that black holes have huge entropy. In fact, it turns out that black holes have the most entropy possible in a given volume. So all the information that went into a black hole gets scrambled, though not destroyed. Remember, entropy is hidden information, scrambled information. However, when the black hole evaporates, info seems to get lost from the universe. It seems to have disappeared. What happened to that information? Well, Susskind and Gerard 't Hooft argued that our information is not destroyed. It must get out. It must be carried by the Hawking radiation, though the exact mechanism might indeed be complex. They just felt that a violation of quantum mechanics was so terrible that it could not be possible. In 2004, Hawking agreed with Susskind, 't Hooft, and some of the others. Information is not destroyed during black hole evaporation. He published one particular mechanism for this in 2005, having to do with quantum fluctuations at the event horizon itself. So Hawking conceded his bet with John Preskill and gave him an encyclopedia of baseball from which he could faithfully look up information. Hawking had made a similar bet with Don Page in 1980, and he conceded it in 2007, paying Don Page $1. I guess all these guys were pretty unsure of what the answer would be, so the stakes of their bets weren't really very high. They didn't bet their cat or their dog or their house or their life on it, okay? But Kip Thorne at Caltech, however, has not yet conceded. He's unconvinced that Hawking's mechanism is correct and thinks that information might well be destroyed. I think most experts generally feel that information is probably not destroyed, but the exact mechanism by which it gets out is unclear. Well, one way to gain some sort of understanding of the preservation of information during black hole evaporation is to go back to the membrane paradigm that I introduced in a previous lecture. Recall that from the perspective of an outside observer, nothing ever crosses the event horizon of a black hole. You have infinite time dilation. It takes an infinite amount of time for material to cross. So it's always visible. The material accumulates on a very thin surface just outside the event horizon. You never lose sight of the object falling in, assuming it continues to emit light, even though in its own frame of reference, the object fell in and got crushed by the singularity. So is the object in two places at once? If you throw in a zebra, for example, you don't see it fall in from the outside, but the person falling with the zebra does see it fall, through the event horizon to the singularity. So the zebra seems to be at two places at one time. The resolution to this paradox is that it's entirely a relativistic effect. It's just different frames of reference, and that's what relativity is all about, different frames of reference. In fact, you don't even lose sight of material that was initially near the center of the eventual black hole. Some photons were on their way before that object, say a neutron star, became a black hole, and you see them at time equals infinity, though those particles think, that they're inside. How thin is the membrane, or the stretched horizon, as it is sometimes called, that holds all of the information? Well, we think it's about 1 Planck length, about 10 to the minus 33 power centimeters from the horizon. This is 20 orders of magnitude smaller than a proton. It's very small. The Planck length is thought to be the smallest unit of length over which any details can exist, even in principle. It is a fundamental unit of length, named after Max Planck, one of the founding fathers of quantum mechanics, and it's what one gets if one sets all the constants, the speed of light, Newton's constant g, Planck's constant, and so on, equal to 1. Then you get natural units, which are called Planck units. Okay, from the perspective of the outside observer, the bits of information are stored within this thin membrane, this stretched membrane, with at most one bit of information, which in fact are strings in string theory, per 4 Planck areas, which are Planck lengths squared. So just take a Planck length on a side, that's a Planck area. The information, according to the membrane paradigm, was never inside the black hole. On the other hand, to an outside observer, the membrane is very hot and thermally emits particles. After all, everything that ever was dumped toward the black hole went crashing into a very small volume in this membrane and got heated up. You know, just like when I rub my hands together, they heat up. Well, imagine putting all this stuff into a black hole. It crashes near the horizon and heats up. By keeping track of the emitted particles one by one, all of the information is actually retrieved. The spectrum is thermal, black body, only statistically. The information apparently is still there. Quantum mechanics is saved. Well, after Hawking conceded his bet with Preskill, he joked, "I gave John an encyclopedia of baseball, but maybe I should have just given him the ashes." You know, in other words, although the information does get out of a black hole, it has been fried and scrambled. It's just a bunch of ashes. It's in a state of maximum entropy. So that's the kind of encyclopedia he should have given to Preskill. So given this statement, I was actually surprised a few years ago when Hawking said in a public lecture at Berkeley that you shouldn't despair if you fall into a black hole because you will eventually get out of it. Well, yeah, you'll get out of it, but you'll have been fried. You know, you won't retain your identity. The information of which you consist will have been scrambled. So my advice is, you know, don't fall in, okay? Don't fall in. It's bad for your health. So let's take a moment for a more lighthearted look at some of what we've learned here. Black holes are crazy places. They just draw you in and hold on fiercely. You know what people say. What happens in black holes stays in black holes. Well, not always, apparently. The information may leak out through Hawking radiation. This is not to be confused with Raider Nation, although they both do involve black holes. Oakland Raiders with the black hole zone. All right, well, let's go back to the membrane, or the stretched horizon. Since all of the information inside the black hole can be thought of as being on this thin, two-dimensional membrane surrounding it, this is kind of like a hologram. Now, a hologram is a two-dimensional plate of glass or other recording device, which, when illuminated, shows a very realistic three-dimensional image. They are even sometimes used on credit cards. You know, you hold the credit card, you can see this image in it. All right, there's the hologram, and if you shine light on it, you get these three-dimensional images. They often look very realistic. Look at these women. I mean, just, you know, really quite realistic. And these guys here, you might think you're looking at the actual people, but you're really looking at a hologram of it. Holograms are made in an interesting way. Light goes through a beam splitter, and one beam hits an object. Light bounces off the object toward a photographic emulsion. The other beam from the beam splitter illuminates the emulsion, and an interference pattern forms in the hologram. If you now shine light on the hologram, you can see the three-dimensional object again. By shining light on a sequence of holograms, you can even make a 3D movie. The action simply changes with time. So, for example, a whole bunch of holograms of this dancer would show the dancer dancing. One of the first uses of a talking, moving hologram was in the 1976 movie Logan's Run, starring Michael York. There's a point where he says, his hologram actually says, "There is no sanctuary." Well, that's perhaps very appropriate because you won't find sanctuary in a black hole. Okay, don't go in one. Michael York, there is no sanctuary. Okay. Back to black holes and their implications. The horizon or boundary of a black hole contains all of the information that ever went into the black hole. So how about a more familiar example? Susskind estimates that the volume of the great library, the ancient library of Alexandria, could have, in principle, held up to 10 to the 109 power bits of information. But if the true maximum information content is only proportional to the surface area, then it turns out only to the 74th power bits of information would have been in that library. That's still a vast amount of information, but it's an infinitesimal fraction of 10 to the 109th power. Mathematically, when the information density is high, the total information does not grow in proportion to volume, but rather in proportion to surface area, not volume. Now, this is unlike normal substances like glasses of water or bricks. Normally, if you have 2 bricks, they carry twice the information content of only 1 brick, right? Well, that's true at low information density, but apparently it's not true when the information density is very high. This weird aspect of black holes is probably teaching us something fundamental about the workings of nature. Certainly this has been a great surprise stemming from attempts to develop a quantum theory of gravity. Well, since black holes contain the most information possible in a given volume, and that information can be described by a two-dimensional hologram, the membrane, one can conclude that any smaller amount of information in a given volume can also be described by a 2D hologram at the boundary of the volume. There's less information, so it's even easier to describe it with bits on the 2D surface. Well, if any given volume within the universe can be described by information at its boundary, can we apply this concept to the entire observable universe? The contents might be described by information plastered in Planck areas at the visible edge or horizon of our universe. Holy moly! Now, the visible edge or boundary is just the distance from which light has had a chance to reach us, traveling for about 13.7 billion years since the Big Bang. It is called the light horizon, and it's actually now about 46 billion light years away, more than just 13.7 billion, because the universe is expanding. It stretches out space during the time that the photons have already been traveling, so you get more distance than you might have thought. So the location of the horizon is changing with time as the universe expands. Moreover, it depends on the observer's particular position. My light horizon observed from here is a little bit different than my light horizon observed from a slightly different place. So for these reasons, I don't think many serious physicists think that there's some physical hologram at the horizon, like some giant machine clanking away. There's nothing sitting around there, no robots. Rather, it's thought to be a mathematical correspondence which leads to these amazing conceptual insights. It's a new way of thinking about the world, and who knows what it will lead to. This holographic principle is a stunning new idea that really is revolutionizing physics. For example, some physicists are finding that a three-dimensional theory of gravitation may perhaps be expressed as a two-dimensional quantum theory without gravity, yet it still correctly predicts phenomena such as black holes and gravitational waves. Well, are there any observational tests of this holographic principle applied to the universe? If the universe really is a hologram, it turns out that indeed there is a test. It should be fuzzy. The reason for this is that there are clearly more Planck volumes within the volume of the universe than there are Planck areas at its horizon. For example, consider a cube 10 centimeters on a side. There are 10 times 10 or 100 square centimeters of area on each face and 6 faces for a total of 600 square centimeters of area. But there are 10 times 10 times 10 or 1,000 cubic centimeters of volume. Now 1,000 is bigger than 600. Not much bigger, you might say, but the discrepancy increases with size. If you have a cube 10 to the 10th centimeters on a side, then each face has 10 to the 20th square centimeters, so the total surface area is 6 times 10 to the 20th square centimeters. But the volume is 10 to the 10th times 10 to the 10th times 10 to the 10th, or 10 to the 30th cubic centimeters. 10 to the 30th cubic centimeters is a lot bigger a number than 6 times 10 to the 20th square centimeters, okay? So the true bits of information in the universe must be larger than the Planck volume, Planck length cubed. Even the quantum fluctuations of empty space could be larger. Every bit of space is continually fluctuating due to quantum physics, due to the uncertainty principle. But the size of the fluctuations should be larger than previously thought. This can actually be thought of as an intrinsic graininess of space-time. Now, Craig Hogan, a collaborator of mine at Fermilab near Chicago, predicted that this quantum foam would be large enough to detect with modern instruments. And is there any, instrument that can detect it? Remarkably, there's some very tentative but intriguing evidence that these large quantum jitters have in fact been detected by an experiment called GEO 600 in Germany. It's a gravitational wave detector, kind of like LIGO, which I discussed in detail in Lecture 7. You've got these two beams in sort of a square pattern, the sides of a square, and inside there are long tubes through which laser beams go, and they reflect off of mirrors that are attached to masses. And you will remember the principle that if a gravitational wave goes through, it should alternately stretch and squeeze the two arms, the two perpendicular arms. You will get slight variations in length, and if you measure the interfering light in vacuum tanks, all this is done in a vacuum, then in fact you get some detection of gravitational waves in principle that way. It's never been done, but we hope it'll be done soon. Well, what the GEO 600 experimenters have found is that despite their best efforts so far, there's a small amount of unexplained noise in their system, a signal that shouldn't be there, but it quantitatively matches Craig Hogan's predictions. They weren't even looking for Hogan's effect, but they noticed it. Well, that is really amazing. This is still a very speculative discovery, of course. In a way, it's really, way too early to know for sure whether the noise seen by GEO 600 is indeed what Hogan predicted. There are still other possible sources for this low-level noise, and gravitational wave detectors are notoriously difficult to fully characterize. But if it is quantum noise, then it's an important, really, really important discovery. So stay tuned. Well, to summarize this lecture, it appears that black holes don't end up destroying information after all. This is good news. It means that a basic principle of physics is still alive and well. This also represents an important step in reconciling quantum mechanics with general relativity. The conclusion that all of the information in a given volume can be entirely represented by a hologram on the 2D boundary is just astonishing. But though the mathematical correspondence is fascinating, I don't think that you and I and everything else in our three-dimensional universe is just an illusion coming from some 2D surface far away. I certainly hope not.